Welcome everybody to the presentation of our talk about the paper cuDTW++ ultra-fast dynamic time warping on CUDA-enabled GPUs. This is a joint work of myself, Bertil Schmidt from University of Mainz and Christian Hundt from NVIDIA AI Technology Center in Luxembourg. So let's start with a bit of background about dynamic time warping, or DTW. Is an important computation pattern or parallel computation pattern widely used for processing time series. So the basic algorithm finds kind of the optimal alignment of two time series. And this is a very similar algorithm to the optimal pairwise alignment of DNA sequences, for example, like the Smith-Waterman algorithm, with the difference that we deal here with real valued data and use Euclidean distance to compare two values. This is based on dynamic programming and has a dependency relationship when computing a DP or dynamic programming matrix where value depends on the left neighbor, upper left neighbor. And we have observed that previous CUDA implementations of DTW are not optimal or not efficient. And in this paper, we propose cuDTW++, a new, highly efficient CUDA-based dynamic time warping kernel, which is based on warp intrinsics for fast communication between threads and can achieve, as we will see, close to peak performance on modern GPUs. It's also publicly available on GitHub. Some more background about dynamic time warping. In dynamic time warping, we basically set up a DAG, a directed acyclic graph, which is of a quadratic size, so n times m, where n and m are the length of the two time series that are compared. Here in this example, we have two time series of length 4, so we have a 4 by 4 matrix, and it's weighted matrix, so weighted DAG. So each node in the DAG has a weight, which is the difference between the time series values at that position squared, so Euclidean distance. And in this DAG, we want to walk from the upper left corner to the lower right corner and find the path which has the highest accumulated weight. And this is called the optimal warping path. And often we are also just interested in the cost of the optimal warping path. And the cost of the optimal warping path can be computed by dynamic programming. And here we see the recurrence relation of the dynamic programming computation, where you compute a two-dimensional matrix M, and the value J prime in this matrix can be computed by choosing the minimum of the left neighbor, and upper left neighbor, and add the weight at that position to this minimum. And here I also have an example of this computation. And initially the first row and the first column initialized with infinity, except for the upper left value, which is 0 initially, and then the cost of the optimal warping path is stored in the lower right value. And the warping path itself can be reconstructed by a traceback procedure. Bit of background about related work and wavefront relaxation. So in wavefront relaxation, you kind of use the dependency relationship of this dynamic programming computation where you have the dependency of a value of the left neighbor, upper left neighbor, and then you can compute minor diagonals in parallel. So these diagonals here in blue, each value can be computed in parallel, for example, using a different thread. And in previous work, and also in this work, we will use one CUDA thread block to compute one diagonal. In our work, a CUDA thread block would just consist of a warp or even a subwarp. In previous work, related work, CUDA-DTW, the state-of-the-art CPU approach for dynamic time warping. Zart et al. Were the first to parallelize that on CUDA, but they do not use a CUDA thread block. They just use one CUDA thread per dynamic time warping score calculation. So this is highly inefficient due to excessive global memory accesses. Then wavefront parallelization scheme was proposed in the CUDA-DTW software, and the paper can outperform Zart et al. By over 1 order of magnitude. And in this CUDA-DTW, each CUDA thread block computes one DTW score, whereby threads compute cells along the minor diagonal in parallel, and the necessary data transfer is done through shared memory. So in this work, cuDTW++, we also use a wavefront, but we eliminate the need for storing intermediate values in shared memory, and instead we are using, we do not use shared memory at all, we just use thread local registers to store the data, and communication is performed with warp shuffles. Here a bit about the warp shuffle. So the important warp shuffle operations in this work is shuffle down sync and shuffle up sync, where you can move a value stored in a register of a thread to other threads, so either to down or up. So important here is to the left neighbor or to the right neighbor, and this can be done with this single instruction. This is much faster than shared memory. So our parallelization strategy, again, we compute a single score, dynamic time warping score per warp or even subwarp if we use less than 32 threads. And the threads in a warp cooperate to compute all values of the DP matrix in parallel. We use full in-register computation for the computation of the recurrence relation that I've shown before. Low latency communication of neighboring DP cells between threads through warp shuffles. And this replaces, we also replace frequent loading of time series values from memory by means of a communication scheme based on warp shuffles. And to support arbitrary time series lengths, we have a partitioning scheme. In addition, we have an early exit strategy based on warp level collectives and atomic variables for subsequence. Here is a diagram about illustration of the mapping of DP matrix cells, computation of them to threads. In this example, we have P threads of a warp or subwarp, and we compare time series Q and SI, and we use here K equals 4, so this is an important parameter. So 4 cells per thread of the current row are computed at the same time. And in this example, these are the red cells. And to compute the red cells, we need the blue cells of the previous row and also some values of the row before the blue row, which is this gray colored cell. And most of the computation can be done without any communication with thread local registers. And the dotted lines, these are communication between threads, and this is all done with warp shuffles. The two time series compared are yellow, so the time series S and the green time series Q. Note that the time series Q also needs to be communicated with warp shuffles in every iteration step. Here again, a partitioning scheme to support arbitrary time series length. So the number of registers per CUDA thread is limited to 256. So in order to support arbitrary lengths, you need a partitioning scheme where you output the rightmost column to shared or global memory and then read it again in the subsequent step, as illustrated here in this diagram. Let's have a look at performance evaluation. So the first evaluation is a database scan, where we scan a data set. This is called the cylinder bell funnel data set, which is well known in the data mining community, using queries of different length. And in the upper left picture here, we determine the efficiency of our kernel for various values of k using 32 threads and using different time series length. And you can see that if you increase the value of k, you have more internal computation while the amount of communication remains constant. So when you increase k, you get a higher efficiency, and for k equals 32, you actually can get over 95% of the available performance of your hardware. This all includes data transfers over the PCI Express. And this is based on a GV100 GPU, and we use CUDA 10.2 with C++. And then we also compare the performance in the table here to the previously fastest program, cuDTW. And you can see that we can achieve speedups of between 15.9 and 12.2. Both software is executed on the same hardware. Another performance evaluation, subsequent search. There you do not have many independent time series, but you just have one very long time series, in this case an ECG signal of 22 hours, streamed ECG signal, and then you want to find out a subsequence or sub time series which is most similar to your query. And we compared the runtime for that with cuDTW++ compared to the state-of-the-art CPU program UCR-DTW, and we can achieve here very significant speed up also with the early exit version that we have implemented of over 5,000. Conclusion. In this paper, we have introduced a fine-grained parallelization strategy for dynamic time warping, which can achieve close to peak performance on modern GPUs. I've presented results for Volta-based GPUs. Very high, similar efficiency can be also achieved on the new Ampere GPUs, which we have also measured in the meantime. We employ thread local register files as a cache, which removes the bottleneck of previous implementations which use shared memory, for example. And data is communicated through low latency warp level collectives. We propose a partitioning scheme and an early exit strategy for subsequence search. And we can outperform state-of-the-art algorithms on the GPU by 1 order of magnitude and on the CPU by 2 to 3 orders of magnitude. It's publicly available on GitHub, and the approach can also be extended to other DP-based algorithms like what I mentioned before, sequence alignment for DNA. Thank you very much, and I'm happy to get some feedback on the paper.